Venturing beyond the real, introducing complex numbers. Mathematics constantly pushes the boundaries of our understanding. For centuries, real numbers were believed to be sufficient. But new challenges required a new kind of number. Enter complex numbers, expanding mathematical horizons. Imagine a number line, stretching infinitely. Now, picture a second line, perpendicular to the first. Together, they form the complex plane. Complex numbers inhabit this expanded realm. Denoted as a plus by, they unlock deeper mathematical understanding. The heart of the matter, unveiling the imaginary unit E. At the heart of every complex number lies a fascinating entity, the imaginary unit denoted by the symbol E. This seemingly simple symbol holds the key to unlocking the unique properties and capabilities of complex numbers. But what exactly is I, and why is it so special? The imaginary unit I is defined as the square root of -1. This definition might seem counterintuitive at first because we are accustomed to real numbers, where the square of any number is always positive. However, I breaks free from this constraint, venturing into a realm where the impossible becomes possible. The introduction of I might seem like a mathematical trick, a way to force solutions where none seem to exist. However, the implications of this seemingly simple definition are far-reaching. The imaginary unit I is not merely a placeholder, but a fundamental building block that allows us to construct an entirely new system of numbers with unique properties and applications. The power of I lies in its ability to bridge the gap between real and imaginary numbers, allowing us to represent quantities that oscillate, rotate, or exhibit wave-like behavior. These characteristics make complex numbers indispensable in fields like electrical engineering, where they are used to represent alternating currents, and in quantum mechanics, where they are crucial for describing the wave function of particles. Exploring different forms of complex numbers. Complex numbers, like multifaceted gems, can be viewed in various forms. The rectangular form, a plus by, is intuitive for basic operations. The polar form describes a complex number by its magnitude and angle. The exponential form, re-ith, connects complex numbers to trigonometry. Section 4. The building blocks, performing operations on complex numbers. Just like real numbers, complex numbers can be added, subtracted, multiplied, and divided, allowing us to perform a wide range of mathematical operations. These operations follow specific rules that ensure the result is always another complex number, maintaining the consistency and integrity of the complex number system. Addition and subtraction of complex numbers are straightforward processes, performed by treating the real and imaginary parts separately. Imagine adding or subtracting two-dimensional vectors. The real and imaginary parts of complex numbers behave similarly. For example, 2 plus 3 I plus 1 minus I is calculated by adding the real parts, 2 plus 1 equals 3, and the imaginary parts, 3 minus 1 equals 2, resulting in 3 plus 2i. Multiplication of complex numbers involves using the distributive property, much like multiplying binomials, but with an added twist. We need to remember that I squared equals -1, which arises from the definition of I as the square root of -1. This property introduces a fascinating interplay between the real and imaginary parts during multiplication, leading to results that might seem counterintuitive at first but are entirely consistent within the framework of complex numbers. Division of complex numbers, while slightly more involved, follows a systematic approach. The key is to multiply both the numerator and denominator by the complex conjugate of the denominator. The complex conjugate of a complex number, a plus by, is a minus by. This multiplication achieves a remarkable feat. It transforms the denominator into a real number, making the division possible. Complex numbers, though abstract, have a myriad of practical applications across various fields. In engineering, they are used in signal processing and control systems. In physics, they help describe wave functions and quantum mechanics. Even in computer graphics, complex numbers are essential for rendering fractals and other intricate patterns. Their versatility and power make them indispensable tools in both theoretical and applied sciences. As we delve deeper into the world of complex numbers, we find ourselves on the brink of new dimensions. Beyond the two-dimensional complex plane lies the realm of quaternions and octonions, extending our understanding of numbers into higher dimensions. These advanced constructs open up new avenues for exploration in mathematics and physics, offering insights into the very fabric of reality. The journey into these new dimensions is just beginning, promising exciting discoveries and profound implications for our understanding of the universe.